he developed the relativity theory, the classical relativity, Galileo not only showed how the movement of the reference system affects the movement of an object or its rest condition, but he also took for granted that the instant is not affected by this change in reference system. That is, time is universal in all the universe. This idea of a universal time has been used by all other classical scientists, beginning with Newton, who developed the classical mechanics. In the 19th century, it has been shown that this is incompatible, classical relativity is incompatible with electromagnetism, both theoretically by Maxwell and experimentally by Michelson. We will show this incompatibility with a modern experiment that is being realized every day with our mobile phones using GPS. GPS is for global positioning system using a constellation of satellites, and we will understand how it works, presenting the Earth as our face and the satellites as a constellation of more than 30 points around the Earth at a distance of about 30,000 kilometers. In this distance, they send signals all the time that travel during 1/10 of a second before they reach the Earth. We will use only 2 of those satellites at the opposite positions to show how they work. They send the signals at the same time, at the same instant, and the signals travel until they arrive at a certain point on the Earth. Let's suppose that there is our receptor, and it knows where we are because he receives the signal at the same time from both satellites. Now, we know with Galileo that the Earth can be in movement at a speed of 30 kilometers in a second. In this 1/10 of a second that the signals travel through space, the Earth moves 3 kilometers. So, if we repeat the experiment but with the Earth in movement, then we will show that the signal will not be at the same time as if it were at rest. And the Earth can be moving in relation to the satellites in all directions, so that this error of 3 kilometers would be all around our position, and it would be very hard to resolve this problem, and the GPS works without taking that into account. How can we show that in space-time, using our hands again? Well, we will show how to represent the instant in 3 different ways. We have seen that the instant is a horizontal line in space-time. That means that in every point the time is the same. Let us suppose this is the instant of time 0 everywhere. Another instant would be, for example, time 1 everywhere. But we can also represent the Earth as before, and this is time 0 for Earth, and this is time 1. But for the satellites, this is also time 0 at the same horizontal distance, so that the signals travel diagonally in 1/10 of a second. We can also represent the instant as 2 satellites sending their signals at the same time from the same distance to the Earth that is represented by our body in space-time, remember, so that if we are at rest, the signals arrive diagonally at our nose. But if we are moving, and the instant keeps horizontal, the signals will not arrive at our nose, but at different eye, at our eye, for example, 3 kilometers around the nose. So, how can we solve this problem? We must keep with those ideas and leave one change it. The Earth is at rest or in movement. If we think that the Earth is at rest, there is no problem. GPS works perfectly. But if we think that the Earth is moving through the universe, then we must try to find also how the instant must change to be in accordance with the experiments. To remember this experimental evidence against the universal instant, we will show it in a sentence. There will be errors in GPS if time were constant at the universe. Now singing. There would be errors in GPS if time were constant at the universe.